So it's my great pleasure to welcome Grigore from Urbana-Champaign. I was visiting him back in December this year, but also early, a year ago, basically a year ago. Both times he took me to his startup called Runtime Verification. So a year and a half ago, there were 5 people in empty offices and on the second floor or something like this. And then in December, it was 35 people in full office and packed in offices, much bigger offices, but on the top floor. So it's exciting times for Runtime Verification, so we'll hope you enjoy the talk.
Thank you, Nikolai. Yes, so I will talk about recent work we do in my group at university and in my startup, Runtime Verification. I do not want to bore you with cryptocurrencies, whether they are the future of money or not. Actually, I don't know, and I'm not qualified to talk about that. The only reason I mention them is because they are one of the main applications of the blockchain technology, and probably also what pushed the interest in this field quite a bit. Also, I'm not going to explain the blockchain technology in depth here. All I want is to give you a quick, broad overview and to emphasize the parts that we care about and the parts where our contributions take place. So for the purpose of this talk, let's assume that a transaction is any code, right? So you execute some code, that's considered as a transaction. And that code is public, it's given, everybody knows it, and it operates on a big shared state, right? So if you want to modify the state, the code, you can just do it. The whole point about the blockchain is that it is not centralized. So there are lots of different nodes, and these nodes need to somehow achieve consensus, what happened. And in order to do that, they need to re-execute the code, re-execute the transaction on each node, and then they have to basically validate the transaction or the result of executing that code. And once they do that, then they deploy the result of this transaction locally in a block, and they append that block at the end of a chain of other blocks, like a linked list, and that's where the name blockchain comes from. It's also called the distributed ledger, and there are algorithms under the hood that achieve consensus, making sure that all the nodes have pretty much the same view of the blockchain, and that's not something I'm going to talk about. I'm only going to talk about how we write programs in.
When you say that it's a transaction, you mean an execution of a
yes,
program?
yeah, you execute a program, and that program modifies the shared state.
So, but the transaction itself is specified how?
Right, so that's a discussion in itself, a long discussion in itself. But somehow you have to invoke a code, and you have to tell a node that I want to invoke that code, and then the node will make sure that the transaction or the command is distributed, is broadcast, and everybody agrees on. Right, what I really want to focus about is that code that we execute in the transaction. Some of these transactions, actually, I had that picture where you transfer money from one hand to another, but in fact, some of these values that you transfer or that you put in this account, they can be programs themselves. And that's where things get interesting, because once you have a program, such a program in your account, then anybody can invoke that program or functions in that program. And for some reason, these are called smart contracts, and as we all know, they are neither smart nor contracts, but that's how they are called. But in the end, all the code is public, can be invoked by everybody, and it can irreversibly change the history. So in particular, if you write one of these functions, you want to transfer money from somebody in your account, but you make some mistakes and the money is transferred from your account to the other account, and somebody invokes it, then your money is lost forever. There is no way to go back. And obviously, hackers now have a huge incentive to exploit such bugs, and they do. So the challenge then is how to prevent these things from happening, and that's what my talk is mostly going to be about. Yes.
Perhaps it's just a nitpick, but I don't don't see it necessarily as changing the history as being able to add a new entry in the log, affecting the future perception of.
Yeah, so all these transactions, all these blocks, they incrementally modify the state of the whole system, which is all the accounts with all the values and so on.
They don't have the ability to change what's in the log. The log
No.
is irreversible.
Right, right, exactly. That's the log is reversible, yeah. All right, so with this slide, I just want to show you that these smart contracts, they are programs like any other programs. The programming language is less relevant, and this is one particular template. Many of these contracts are very simple. Imagine like 500 lines of code. 500 lines of code is already a large program considered in this domain. And this language, Solidity in particular, is not a great language. But that's not my point of my talk. My point is that this is an ordinary program which implements a function transfer, where you transfer to a certain address. You are supposed to call that function. This function is somebody else's account, and I want to transfer money to that account. Then I call their transfer function, and I say where to transfer the money and what amount, what value. And then it's just code as usual. You check if the amount is 0. And if, actually I should have not shown that. If it's 0, then you return. Otherwise, if it's not 0, then you check the balance of the sender to make sure that you have enough money. And if you have enough money, and you also check, make sure that there is no overflow on the other side. If there is an overflow, then things can happen, and you'll see bad things can happen. And then if I have enough funds and no overflow, then I do the actual transaction. So message sender is the actual address of the account that transfers the money. And there is cryptography happening under the hood, which again I'm not going to talk about. And how consensus is achieved, again I'm not going to talk about. This is what we are going to talk about, programs, right? So it becomes just normal program verification as we know it.
So the capital transfer is a Solidity construct, or is
No, this is just a program that you write.
the one
That's the fourth line from the bottom.
yeah, the one before true, return true.
Oh, this or transfer.
Now the capital transfer.
Capital
is that a-
transfer.
that's a log event, or is that a function?
This is well, so this is part of the library. It comes, so many of these transactions are logged, so they can be audited later on. Right, but you're not supposed to code it necessarily when you write programs.
Function call is logging the transfer. It's not calling the function, right? It's just adding that as a log event.
Yeah, it's a log event. It's an event. Yeah. Right.
When you say 40,000, is that on Etherscan?
Yes, Etherscan.io. There are 40,000 similar snippets. They all try to implement this template called ERC20, which is just a simple protocol to transfer money from one account to another. Interestingly, if you try to read the specification carefully, you'll see that there is no clause in the specification saying that you should return if the value is 0. Actually, some applications may rely on that event is logged, right? So you can check it later on and so on. So actually, this code is wrong from that point of view, and it is wrong from another point of view, that it checks for overflow, and if it's overflowed, then if an overflow happens at the receiver, then the transaction is not, or the transaction is not applied. However, there is nothing to stop you from transferring money to yourself, and in which case there is no, you may wonder why should you do that, but actually there are attacks which happen exactly that way. So if you transfer money to yourself, you create new money. So it's like, you want new money, it's like having a printing machine in your garage, right? Just transfer money to yourself and you create new money out of the blue. Right? There are contracts like that. Not this one, but you have to take into account this. What if I transfer to myself? You transfer to yourself, then you have no overflow. And actually, this program is incorrect from that point of view too. All right. So nothing critical with that, but there are other attacks which are really, really very funny, like this one, the beauty coin. There is a batch. They have a more complex transfer command called batch transfer, where you get a whole bunch of receivers and you want to transfer a value to all of them. All right, and what this does is to, you see how many of them are there, then you calculate what's the amount that you should subtract from your account, make sure that you have enough balance, enough money, and then if you do, then you subtract that amount from your account, and then you transfer the value to each of the receivers. Right? It may look completely innocent, but there is a huge problem with this, and actually that problem led to the termination of this business. This particular company died because of this bug. And you know what the bug is? It's right here. You can invoke this function yourself. You know, if you are someone in Zimbabwe, you can simply invoke this function. And if you pass the right value here as an argument, then you can make this multiplication overflow. And if it overflows, then amount becomes a huge negative number. And what happens when you subtract a huge negative number from your balance? You get a huge positive balance in your account, right? So that's what the attackers did. They ended up creating so many coins that was the equivalent of 10 to the power $70. It's not like $1 million or $1 billion. It was literally more money than ever, and obviously they never could get that money out. What happened was that they destroyed that particular coin, right? So it's not like you have a $1 million bug in your code anymore, right? It's the all or nothing. All right.
I don't think that they can. If they export this underflow, they have to create this amount.
And then the due to the 250 number.
Yes.
Beauty coin?
Yes. It's one coin, but the same bug actually happened in lots of accounts. When this happened, an exchange had to freeze all the ERC20 transactions. They not ERC20. I think this has it's a variation of ERC20, right? So they had to freeze they basically, had to freeze the entire business for a while until things calm down and they figured out what to do. Okay, so bugs have huge consequences. And there are lots of others. I'm not going to bore you with them, like the DAO exploit, the parity bug, which actually froze $280 million. Then they fixed the bug, and they had a fixed version of the contract, and then 1 or 2 months later, it was attacked again, another $300 million frozen. And it's funny that you actually know who did it, right? You can go to this, you can see the exact address, you can see the exact code, everything is visible. You know exactly how the attack happened. Of course, you don't know who this guy is, DevOps 199, but you can see exactly his attack vector. All right, so the reason I showed you this slide is just to bring the problem back to program verification. In the end, you have programs that need to be verified. Programs which do the wrong thing and then things go bad. So we need to use verification. What can we do? Programming language, formal methods people do about it, because there are lots of things that can be done about the entire field, right? At the economical level, political level, and so on. But we cannot affect that right away. So let's look at what we know: programming languages, execution environment. What can we do there? How can we improve things there? And I firmly believe that actually in this particular field, because the programs are not that big, we can go for the ideal scenario, right? We can go directly for everything verified. And what do I mean by that? Is that everything must be rigorously designed first place, then all the implementation should be provably correct. And now if we try to split things and look at where these things appear, so first of all these VMs in the different nodes, they should be provably correct, and they can be provably correct. Because if some of the nodes run a different version of the VM and get a different result, then they get different results, consensus doesn't happen, forks appear, and so on and so forth. Then the smart contracts themselves, they should be written in good programming languages, not like Solidity. Then the compilers and interpreters for these languages should be provably correct, so things don't happen under the hood. And finally, the smart contracts themselves should be formally verified in whatever language they end up being written. And I think all this can be done. And since there are so many languages going on, I only showed you Solidity, but there are lots of different languages, more abstract, more concrete, higher level, low level, VM languages. So when we see all these languages and lots of provably correct around, we think of a language framework. It would be nice to have a language framework in which all this can be done. And I have been preaching for many, many years this idea of an ideal language framework, which basically means that for any programming language, no matter how complicated that is or how simple it is, right, we can have one formal definition, one formal semantics, and syntax, basic definition, formal definition, including syntax and semantics, one and for all. And then all the tools that we need for that language, parsers, interpreters, compilers, debuggers, symbolic execution engines, model checkers, deductive program verifiers, everything should be derived, should be given to you by the framework for your language. In other words, you plug and play your language into the framework. You want Solidity, plug Solidity, and now you have all the tools for Solidity. Yes?
So that's actually my question. So you can't do this for Solidity, right? Will this be
Unless you have a formal semantics.
crazy semantics?
Yes.
With overflows and stuff?
Yeah. Then you verify programs with overflows and crazy semantics, if that's what people want.
Oh, right. So that would
Yeah,
actually
yeah. You don't try to fix the language if that's the language they want. Of course, I do believe that people should design programming languages this way from the beginning, and then to have better languages. But even if we have to take the languages that are there now, we can still do this and get all the tools for them.
still help because
Yeah.
it's now verified. And
Exactly.
overflow, right?
Yes.
Well, theoretically, there is a semantics. You just have to look at the compiler code, right? Look at the C++ code.
Yes, but I also want to do all these things automatically. I want all these blue boxes to be given to me by the framework for free. I want a symbolic execution engine. I want a model checker, a deductive program verifier for the same language. If you can extract those from the compiler, then yeah. All right. And I'm not saying that we have that framework. I'm saying that we are trying hard to achieve that. That's where all our research goes into, both in my group at university and in my company. And we build things around the K framework, which is open source, public, and we encourage people to contribute and help. And there are lots of groups now defining formal semantics in the K framework. This way they discover bugs, and we fix them and so on. So what is K? Well, so how it took birth, first of all. I've been teaching programming languages for 20 years now, and there was no doubt for me from the very early stages that we should have operational semantics of programming languages. Right? But what was not entirely clear to me was what kind of operational semantics we should have. And then we studied lots of different operational semantic approaches, like small step, big step, evaluation context-based, abstract machines, and there are lots of abstract machines, chemical abstract machine, which is slightly interesting and different, axiomatic semantics, continuation-based, notational semantics. And then we try to analyze them for their benefits and drawbacks. And also looked at experiments. So there were projects in class, student projects, where I asked students to define a particular language, not IMP, something a bit more complicated, using different operational styles, and then to see where people run into problems. And based on that, we actually engineered a framework. Right? So we engineered a framework that would collect the benefits of the various operational styles and at the same time avoid the limitations, which is different from coming up with some theory up front and say that I really want to implement this theory in a language. That was not the approach. Right? So we engineer the framework to make sure it works, and then we step back and try to understand what we're doing and to come up with a theory. Okay? I'll also show you a bit the theory, but let me first show you a bit how the framework looks like to get a flavor for what's going on under the hood. So this is a simple language called kernel C, defined completely in K, and this is what you generate. This is one of the backends, generates a LaTeX file and then a PDF. And I'm going to zoom a bit through it. So syntax is defined using BNF, conventional BNF notation. But we have some annotations. It turned out that in practice, when people define real languages, you have like hundreds of language constructs. And it makes a lot of sense to define the evaluation strategy of the construct right then when you define the syntax. Right? When you define the syntax, you get the parser, but you can also define the evaluation strategy right then. And most of the roots in operational semantics are around evaluation strategies, how to propagate computation from here to there. And those are very boring, error-prone. So we wanted to have a very compact notation and intuitive for that. So this strict of 2 means that the assignment, which has 2 arguments, is strict in the second argument. So this will become a result. And now I can assume from here on that it will be a result in all the other rules. And the K infrastructure will take care of that. And you can express that in all operational styles, small step, big step, all of them have their own ways to express that. Right? So that's not the point. The point is that, as I said, it should be a practical framework, and that's one feature that was requested a lot by users. Then, once you are done with the syntax, the next step is the configuration. You need a program configuration, something that holds everything, holds the computation, the heap, the environments, everything. And here we borrow this idea of solution from the chemical abstract machine or the gamma language early on, where basically you have all the semantic components floating, and they can be nested. Here there is only one level of nestiness, but you can go really deep in many cases. And each of these holds some sort of information, and the order doesn't matter, right? So the principle is based on, the computation principle is based on matching. You match the things you need, and then things rewrite to something else, right? So there is a way to specify this configuration. And then rules simply match what they care about and apply their transformation. For example, the assignment, again, it's a super trivial language, right? So you only have an environment that binds variables to their values. And what you want to say for assignment in such a language is that, first of all, the assignment must be the first task to evaluate. This is set here. You see, notice the K cell has this zigzag is torn there, meaning that there is more stuff there, but I don't care about. We call that a structural frame. And in the environment, there could be more stuff before and after the binding of X, but we don't care about that either. And we don't care what the value of X is now anyway, because we are going to rewrite. Right? So this is the context. You first write the context, and then you underline the things that change. Like the assignment will change into V, and the value here will change into V. And in ASCII, you write it like this. So there are two rewrite relations in the same rule. Right? So we push the rewrite with where it actually happens. And that was extremely practical and modular in real life, because many rewrite rules or many semantic operational rules are like, you have a huge configuration, and then you modify it to another huge configuration, and everything stays the same except X, which changes to V. Right? So they can be error prone. You forget a sigma, make it sigma prime, or we just wanted to not see any of that in rules. So you just use dot dots for things that you don't care about, and you only write the things that you care about in the rules. And this makes it modular and less error prone. That's pretty much it. It's a very simple computational mechanism. You have terms. They are governed by some algebraic structures like sets, maps, lists, and so on. And then you have rewrite rules that match and transform.
Do you ever bind meta variables to the dot dots? And
yeah, it's an essentially quantified variable if you want to do proofs about it.
Tend to also occasionally refer to them. Could I map the dot as a frame Q?
Yes. You can actually write. Instead of this, you can put a variable K or R for the rest of the computation. And some language construct like call CC. If you define call CC, you have to grab the computation and store it in the store. You have to match it then and store it. Yes, you can refer to them.
Variables sorted?
Yes. Yeah. So there are all the non-terminals in the grammar are sorts, and then the variables are sorted. But K also does sort inference for you.
Where are the sorts? They're somewhere here.
The sorts are here. EXP becomes a sort. A non-terminal becomes a sort.
I see.
And you can define additional sorts if you want in the semantics. Right, and this is an important point because also we do not want to write the sorts, so K tries to infer. And the sort inference in K is quite complex because you have several things that are mixed together. The K syntax, your language syntax, and what is a result, what is not a result, and so on. All right, so whenever you see a mathematically rigorous framework, the next thing you have to ask, and you ask, I know, because you're Microsoft, is does it scale? Right, so we believe it scales, and we believe it scales because it has been designed with that in mind from the beginning. So we defined large languages from the very beginning, and we defined them completely. Not a convenient fragment, not 90% or 95%, but complete languages. In the sense that we took benchmarks that compiler developers used to test their compilers, and then we ran them with the semantics. Right? And this way we define Java, JavaScript, x86. Actually, we just finished x86 now, so we can take actual machine code and run it with the semantics. C, that was by far the biggest effort so far, especially because it has 192 different types of undefined behavior. And we have more than 10,000 C programs in the regression, so each time we modify the semantics, we run again all the programs, make sure that they run. But the nice thing about it is that you use exactly that for verification, right? It's not like you have to check consistency with something else. It's exactly the same artifact that you use for the verification.
So with your tool, you'll get the verified C compiler out of it, right?
If you had a compiler, we don't have yet a compiler. Okay, we generate an interpreter.
You only get
The interpreter. We can have the interpreter.
Okay.
Actually, Philip Wader and his team, they compared this with CompCert. They took C. Smith, which generates random programs, and then they compared them, and he found some bugs in CAMSert, but not in the actual. It's always about how you encode a language, right? It doesn't matter that. Right. It could be lots of glue code and so on. Right, and he also found one bug in K, which was not, again, it's not in K, it was in our semantics of K, how we interpreted something in the C semantics.
But K itself, I mean, you haven't developed it as a verified system.
No.
What's the overhead, though, for this interpretation? I mean,
I'll go to that. I'll get to that.
done, right?
Yes, definitely. Yeah, right.
Also, when you say you run these tests, what do you compare? You just compare the return value and then?
No. So we wrap the entire. I will show you how we write it. We wrap it into a drop-in replacement of C. We have a tool called KCC, which is the same like GCC. So learning curve is one letter for developers. That's it. Right. And then you run exactly the test the same way. Actually, you can go and modify your make files to use CCC KCC instead of GCC. So they know nothing about semantics or anything. And we work with Toyota, Boeing, and they just use it. They complain, of course, about performance. They complain about lots of things, but not about mathematics or ease of use. All right. Yeah, we're working on that. Good. And now what we've done recently, we took these languages. So the whole this philosophy of having language parametric framework started to pay off. And that's why we grew to 35 people. Because now all we have to do to adapt to accommodate a different domain is to take the language and give it a semantics. So we took all these languages from the blockchain space, starting with Ethereum virtual machine language, formalized them, and now we have all the tools for those languages. All right, so a bit about C. So C, as I said, was the most complex language. That's how the program configuration looks like, and you see there are many levels of nestedness going on. There are more than 120 semantic cells and more than 5,000 rules, actually, right, in total.
We're going to talk about the x86 work.
No.
Can I ask about it?
Later. Let's discuss tonight or later. Because you gave me only 1 hour. You insisted it should be 1 hour.
I think especially with the Battle of Line.
Yes. Yes.
Yeah, the clock is ticking.
Right. So what I'd like to do next, so again, the philosophy behind the K framework is eventually to have all these blue boxes implemented and provided to the framework, and all of them completely agnostic to your language. What I'm going to do next is to discuss a couple of them, what's inside, and show you some examples how they work.
So can I ask one more, like,
Yes.
to understand better? So now, with, for example, the C definition, now I could have a small C program, it could make a statement about it.
Yeah.
And maybe now you could verify
Yes.
it also.
Yes, you can verify it.
The whole goal.
Yeah, exactly. You can make the statement and verify.
It's like a first step, really.
Yeah. Yes. And I will not stop until that happens. With all languages. Right, so let me tell you how we do interpretation now, because this is by far the most commonly used tool. Right, because you design a language and immediately run programs with it. The parser, obviously, but the parser gets out of the picture quickly, then interpreter is the next. So currently, we have an OCaml backend of K, where basically we take a K definition and generate an OCaml program, an interpreter, and then we compile the OCaml program natively. That's how it works. And we have this tool RVMatch at runtime at the company, and this is the sales pitch of the tool. I'm not going to read it. And this is how it works. Suppose you have a C program like that. Notice that you have a short int here, and you go 16 times, so you overflow it. 15 times you overflow, but it's not really overflow. In C, that's called something. It's a conversion error, right? You convert from something larger into something smaller. And that's an implementation-defined behavior. But anyway, just to show you how the thing works. So if you run the program, if you compile the program normally with GCC and run it, you see nothing. But this program is undefined. Right? This has a problem. If you compile it with Clang, you may get a different result. If you put it on embedded platform, you get a different result. With KCC, you compile it exactly the same way. This is one of the tools in the RVMatch toolkit. Eventually, you want to have model checkers and more. So far, right, so you compile it with KCC, get the binary, and run it. Exactly the same user experience as if you have a normal compiler. But then when you run it, you get this error message, which tells you what kind of error it is. Each error has a unique identifier, and also we give pointers, exact pointers to where the type of undefined behavior is explained in the standard. Why? Because we had several customers who complained that we generate false alarms, and we had to discuss the same issues over and over again, explaining them, and no, go to that section in the standard and you'll see that it's not undefined behavior. And then we decided to just incorporate all these error messages into semantics. And now they get this and they don't bother us. Yes?
This particular example, isn't it a function of your data model, whether this is undefined behavior or not?
Right, so
with
C
short and-
has 4 types of undefined behaviors. And this is implementation-defined behavior. And for implementation-defined behavior, what we did was to take the GCC interpretation for 32 bits or 64 bits. We have plugins, semantic plugins. Yeah, semantic plugins. But nevertheless, we still report the error. We report the error, and then we continue the execution with that particular semantics. Yeah. All right, so since we worked with Toyota, Toyota has this benchmark, the Toyota ITC benchmark, which they create in order to evaluate to evaluate static analysis tools. As you know, these static analysis tools are extremely expensive, and in order to buy a tool, many companies like Toyota, they have a committee which evaluates the various tools, and they have their own benchmarks, programs that they need in their company. Mostly they get from developers, and this benchmark has 1,200 and something tests. Half of them have errors. Half of them try to trick the tools into reporting errors. And yeah, so Toyota evaluated several static analysis tools, and they were looking at defect rates and false positive rates, and then a productivity metric, which is the mean of that. So if you just want to look at a number, for example, CodeSonar, which was their best tool, scored 82, which means that in 82 of cases, we expect to get something meaningful, if you want, from the tool. We just ran the same benchmark with RVMatch, and we got 91. But some of the errors, actually, we don't even check at all because they are not really undefined behaviors. They are just, some of them are just bad coding practices. And many static analysis tools also check those, whether technically they are not undefined behaviors. So that's why we do poorly at that. But what's important to note is that there are no false alarms at all. Right? If we get any false alarm, it means that we have a bug somewhere that we'll have to fix. But there shouldn't be any false alarm. With the KCC tool, which is just a concrete execution engine, you wouldn't expect false alarms there. Just a dynamic analysis tool, basically, where you monitor the C semantics. The specification that you monitor is the C semantics. Right? You can think of it that way. It's runtime verification, where the specification is C.
So is it true that static analysis tools don't require tests, but your RVMatch?
Yes, exactly. Yeah, but Toyota came up with tests as well for all of this because they wanted to test also the dynamic tools, not only the static analysis tools. True, right? So we do worse there when you test.
These tools do runtime verification except RV match?
These tools are static analysis vendors.
Doing runtime verification.
If any of them what?
Are any of the tools other than RV match doing runtime verification?
On the next slide. Sorry. All these are static analysis tools.
Okay, those were all static.
These are all static analysis tools, yes. Like Valgrind is a classic tool people use.
This is dynamic.
Dynamic.
This is dynamic now.
Yeah, it's all dynamic.
So because RVMatch is dynamic, right?
Yes,
Right.
yes, yes,
So you-
exactly.
Discussing the other two.
So previous slide was comparing you
Static,
against
with static,
Okay,
yes.
fine, yeah, got it.
And here,
Well, GCC and Clang is actually running the kit. No, is that the?
no, here
pilot?
just I want, okay, yeah, so the reason I have this is because I gave this talk at NASA, and the developers there said that, well, we don't need any of these tools. We just compile the program with all the warnings enabled in GCC and Clang, and this is what you get, productivity metric of 2026 in that range.
Okay.
Right. And these are the dynamic ones, and we ran the same tests. And all these numbers here show that the model of C was not, the C specification was not properly captured in these tools. That's all it shows.
So the point is if you're green, if you're 100, if you're anywhere below it,
Right, it means that you gave false alarms.
but you have some below 100 on the green on yours, so I don't quite understand. What's the
Which
meaning
one?
of
Here?
that?
This is the defect rate. We missed errors here. And we missed errors because the tests that Toyota provided don't cover the entire code.
And for concurrency, you would rely on race conditions.
For concurrency, yes, we do nothing special. We have another tool dedicated to concurrency errors called Predict. So here we just simply run the program concurrently, and if we happen to run into a data race or a deadlock, then we report it, but that's not very useful when you do, you want a better tool, and we have a better tool for that. So we do poorly at concurrency, yes. And all these three categories. And miscellaneous, those are also not really undefined behaviors.
Wait, so I'm trying to understand. FPR,
FPR is the false positive rate,
right?
and underscore is they wanted to have up to normalize by 100.
Oh,
That's the
I see.
complement.
Oh, it's reversed. Okay, got it.
Yeah.
Sorry. Okay, okay.
And pharmacy, for instance, is it that analysis? What is it searching for?
So they have a value analysis plugin, which is based on abstract interpretation, but is mostly a dynamic analysis. They simply run the program. You need the input.
Only undefined behaviors, or are they looking for other things too?
So all of them, they don't say undefined behaviors. They say that, and ComCert as well, they say that you should make sure that your program is a correct C program before it doesn't have undefined behavior. They don't say undefined behavior because undefined behavior tends to scare people away. Right, but so they are more interested in, like ComCert, in correct compilation once your program is well defined.
So I didn't,
So that's why they provide these tools, so you can run your programs with these tools to filter them before you go to the actual tool they provide.
the concert interpreter, I didn't know there was such a thing. Tell me about it.
The ComCert interpreter, maybe you can tell a bit more about it. So I tell you what I know about it.
Separate, it's a
So ComCert assumes, like all the compilers foresee, that your program is well defined. And then it guarantees correct compilation for well-defined programs.
Yes.
But if your program is not well defined, then anything can happen.
Yes.
Actually, compilers take advantage of
Yes,
undefinedness.
understood.
Yeah.
And the interpreter does what?
And the interpreter checks for undefinedness.
That's the point of the concert interpreter?
Yes, yes,
is to
yes.
do dynamic checking
Yes.
for undefinedness?
Yeah.
But not all these other conditions?
So, from what I remember.
Well, undefinedness, all this undefinedness, all this, every error in C is almost every error in C is an undefined behavior. Like buffer overflows, stack overflow, all these undefined behaviors.
What, yeah, okay.
From what I remember from Xavier, the interpreter extracts the proc semantics to a camel so that he can execute via a camel his semantics, and
Yeah.
then the semantics enumerate all the possible behaviors, especially stuff like side effects within expressions,
I see.
and gets back to you with a list of possible outcomes for the symbolic.
So why aren't we, why isn't concert interpreter closer to RV match then?
Big-
ComCert defines more stuff.
Sorry?
The ComCert, I think, defines more stuff than the system.
No, defines less. It assumes the programs are well defined. It doesn't have to look for all possible crazy undefined behaviors.
That's,
I think integer computations, I think in concert are handled less precisely than in the C standard. Yes. So yes,
I
there,
guess-
that's where
ComCert's
I'm just
job.
thinking concert as a gold standard, so I'm looking at this.
No,
going,
so it's a gold
what's-
standard. It's a gold standard for translation, for compilation. But C, right? So C is this fragment of all the C-like programs. All these programs, the undefined behaviors, they are C-like. They look like C, but they're not C programs. It's only this subset. And this is actually undecidable to detect, even dynamically, to detect whether the program is it's well defined.
Okay,
It's-
so it's not as aggressively checking.
No. So what compilers do, compilers pick a fragment somewhere here,
Okay, yeah, I understand.
and that's what they do.
So the concert interpreter is really honing to the semantics of the compiler. It's not trying.
Right, exactly.
It's a set of assumptions about
Yes.
the well-behavedness of the program.
Yes. Well, what we try to do was to have a faithful semantics of the C semantics for many reasons, not only compilation. Right. Right. So RVMatch, the RVMatch tool we see has been used by several collaborators and customers. And what we really do in the blockchain space is to use exactly the same infrastructure that runs the C programs, but to run programs in a different language, EVM, ELE, Bluetooth. And here we collaborate with blockchain institutions and companies. I'm going to talk about that later, but I'd like to first talk about other capabilities of the general framework, namely verification. But since you guys ask so many questions, I may need to beg for a few more minutes afterwards.
You didn't say the overhead of the interpreter, and how much slower is that?
So in the case of C, it's really scary. That's why I don't want to tell you. In the case of EVM, in the case of EVM, is a lot better, between 10,000 and 100,000 times slower.
Okay.
But the LLVM interpreter itself is more than 1,000, between 1,000 and 10,000 times slower than the native code generated by LLVM. So you expect that from an interpreter in this, when you go to native code. So what we could do, I think the best we can do is to improve things an order of magnitude only, not more than that, right?
Okay.
But I will show you that in the context of blockchain languages, we do a lot better. We are 8 times only slower than the C++ implementation of the VM.
And that's using your backend that extracts to a camel.
Yeah. And now we're actually working on an LLVM backend, okay, which promises almost an order of magnitude more performance. A bit about verification, because this is an important part of what we do in the blockchain space, actually the most important part. So the state of the art is based on defining a so-called axiomatic semantics for your language, where you take your language and regard it as a logic with sequence, where you prove, you derive triples, like Hort triples, like this is the while loop or recursive procedures. And then tools optimizing, extracting weakest preconditions, and so on and so forth, based on these general Hort logic principles. And the problem with this approach is that for each language you need to come up with this somehow, or extract it automatically, but people try to do that. It's not easy. So what we'd like, really, to achieve the vision of the framework is to have a language-independent proof system. I'd like to have something like Hort logic, but to be completely language independent, not to refer to while or procedure calls or anything like that. Just a Hort logic-like a proof system logic, which is generic, not a design pattern. Right? Hort logic is more like a design pattern that you have to use in each language. And I would like that to have all the desired properties. I would like it to take an operation semantics of a language, C or whatever it is, as axioms, so it becomes a mathematical theory in the logic. And then I should be able to derive, now I say reachability, but in the end, any properties about any program in any programming language. And I want that to also come with a sound and complete proof system. And complete in the same sense of Hort logic, relatively complete. If you have an oracle for assertions, but still, we'd like to have these generic results and then to apply them to all languages. And we have that logic now, and I'm realizing that I will not have any chance to go into the details, knowing you, but I can give you a high-level overview of what the logic is about. It's the logic of patterns and pattern matching, right? You saw those configurations, they were like patterns, and you have to match them. And the actual concrete world matches these patterns. And the same pattern can be matched by various values, concrete values. For example, a linked list in the heap can be matched by lots of different instances of pointers that you don't care about, and so on. So what would be a nice logic to express all this? To talk about structure, logical constraints, binders, when you have binders, and recursion and fixed points, because we know we need all this. And the logic we came up with is called matching logic, and these are patterns. So there are no formulae and no terms. I know that may sound strange. They are just patterns, and patterns generalize terms and formulae. You can obtain terms as we know them axiomatically. Add axioms and you'll make them be terms, these patterns. If you want them to be predicates, you add some other axioms and make them predicates. And it borrows ideas from terms and predicates and everything. So this is how we build terms. We can still build terms like that. You have variables and then symbols on top of other terms and build new terms. But then you can also do, and by the way, a term as a pattern is matched by the concrete terms, right, that match it. But then you can also just do logical reasoning with them, say not phi. And that's going to be matched by all the values, all the concrete configurations, if you add, that do not match phi. And then I can have conjunction. Give me one pattern, another pattern, I want the intersection. Right, all the concrete words that match both of these. So with this, now we can do logic inference and reasoning. So structure, reasoning, and then we need binders in general. You have lambda, you have constructs in lots of languages, and functional language also being defined in K regularly. So we wanted to have one construct only for binding. And it turned out that the existential quantifier, as we know it, is actually quite nice. You put an existential quantifier, and that is like an abstraction. Now, you take here the union for all possible values of x, of all the values that, all the elements that match the pattern phi. Has a very nice, clean semantics. All right, that's pretty first order-ish in nature so far. What is different is in models where these symbols are interpreted relationally. They are not interpreted as functions. So this is the syntax. So the symbols are interpreted into the power domain, because these are all the values that will match that pattern. Right? So sigma applied to some values builds a pattern, and now it will be matched by a set of elements. This is the proof system. It has 13 proof rules, and they are mostly borrowed from other logics, like from propositional and first-order logic. And what's nice about it is that you just copy and paste those proof rules, because patterns can be seen as predicates, and they still satisfy all the properties of the predicates, which was quite nice. But what is different with patterns that doesn't happen in first-order logic, but happens in modal logics, is that you can put symbols on top of other patterns, like an always in front of a formula in modal logic. So now you have to worry about propagation of reasoning. If I do reasoning under a symbol, does it propagate? And there are several rules for propagation. Some symbols propagate, like disjunction and existential quantifier. Basically, symbols related to cases, to disjunctions. Where I have cases, I can leave the cases. But others do not propagate. So there are these 3 rules for propagation. This C sigma is the context of a symbol. I have a symbol. I don't care what I have on other positions, but on one position, I can apply and propagate the reasoning.
So you can have a variable appear multiple times and it means the same term.
Yes.
So you have
Yeah.
equality.
Exactly. Yes. The same term everywhere where it appears. The same pattern. I can instantiate with a pattern.
Okay.
Then, interestingly, framing holds. Meaning that if I prove phi1 implies phi2 locally, I can put it in any context. Not only in the heap, like in separation logic. This is just an artifact of a very general principle of framing. Right? So I can put it, give me any context, and now I can put reasoning in that context. So that's what this is saying. And that needs to be a proof rule. Without it, you cannot prove completeness. But it's nice that it also generalizes framing as we know it in other contexts. And all these rules so far make a lot of sense, but these 2, I didn't expect them. They were basically needed for being able to prove the completeness theorem. We couldn't prove the completeness theorem of the logic without this. One is existence. Exists x, x. You cannot write that in first-order logic. Exists x, x means basically that a set of values is the union of its elements. That's what it means, mathematically, which is obvious, but you cannot prove it from the others. You need it as an axiom. And actually, this is our notion of truth. So true is exists xx for each sort. And then this is another interesting and unexpected, completely unexpected.
Yeah, but what about that?
Confused about the exists XX.
Yeah.
If this is reusing, what is the sort of X? It's
Yeah.
it's
Any
both
sort.
an element as well as a...
For any sort. Right, so I didn't show the sorts here. They are in the previous slide. But for any sort, you have a truth for that sort. For natural numbers, I have a notion of truth in the natural numbers, which is actually a pattern which is matched by all natural numbers. I have a notion of false, which is bottom, which is matched by the empty set. No elements match it. And then I can have everything in between. And you can define these patterns and write axioms about them. For example, I can define the pattern of even numbers. And you can define it recursively once I show you mu.
So X is, in that case, interpreted as both an element of the sort and the truth value for that sort.
Exists xx is interpreted as a truth value for that sort. X is interpreted only as a singleton. That's very important, actually. The variables are singletons.
But it's in the truth position here, I think.
Yeah,
That's
yeah,
what you're
yeah.
saying. To the
Here?
right of the dot, what does it mean?
Yeah, so actually, that's the thing. We don't make any distinction between predicates and terms. So this is the syntax. This is the syntax. X is a pattern, and so is exists x another pattern. I know it sounds strange, but once you get used to it, then first order logic for me now sounds too artificial.
I think the key is on the next slide with the power set domain. So
Right.
you
A
interpret
variable,
the power set,
a variable will be interpreted as a singleton.
which gives you an extension for say, satisfiability.
Yeah. Uh-huh.
But your context
So
don't
what's
have
false?
negations.
False.
Yeah.
False is, let's say, to keep it simple, not of exists xx, the negation of this.
Okay.
And if you want to define lambda, I was showing Leo how to define lambda. So lambda x dot phi is actually, you have to add a symbol lambda, which is just a constant, and then you apply it to exist x phi. So this way you separate the fact that lambda builds a binding and a term into its two ingredients. So this builds a term, and this builds the binding. You just have to make sure you keep them together all the time. And I don't want to get into that. Just to show you that you can recover now everything. You can recover terms, you can define equality, lots of things you can define axiomatically.
Is matching up to reduction? Or is there any notion of reduction in here? I'm wondering.
No, there is a notion of proofs. This is how you build proofs, you proof patterns. And reduction, actually K is all about reduction. For reduction, you have to add a symbol next. And then reduction, left rewrites to right, becomes left implies next, right? But this is just a symbol now. And when you define a semantics of a language, you actually define lots of axioms like this. And now with mu, you can define reachability. I didn't show you mu. I'll show you mu now. Right, so finally, so we have constructs for structure, for logic reasoning, for binding. But we also need induction and recursion, we know that, that's unavoidable. And again, we try to look at the essence of things, what is the minimum, smallest thing that we can use to talk about recursion, and that's mu. And for mu, we needed to actually extend the set of variables. Now we have set variables, because with mu, you define fixed points over patterns, which are sets. And then mu is just like this. So you say mu x dot a pattern, and that x is a variable, is a set. And let me show you how to define natural numbers, for example. Say the zero and successor are constructors. The natural numbers is going to be, for now, let's think of an alias, but you can also define equality. Is going to be mu n, where n now is one of those set variables, 0, where 0 is a constant, or successor of n. Right, so you can define constructors, you can define back all the world as we know it, but from a very simple canonical universal logic. And there are two proof rules that govern mu. One is what we call the prefix point. Since we don't have equality, we had to generalize the fact that phi, that mu is a fixed point. So this is saying that mu x phi is a fixed point of phi. If I substitute it for the variable x, I get mu x phi. It's a fixed point. And the Knaster-Tarski. We call it the Knaster-Tarski. We say that if you give me any prefix point, then mu is going to be smaller than it. This is the least fixed point. And when we interpret this in the models, this becomes exactly the Knaster-Tarski theorem, which is quite nice, actually. I'm very happy with that. Right, so that's what gives us hope that this could be general enough. It's general enough for dealing with everything we need in K. All right. And obviously, once you do that, once you add mu, you break completeness. You don't have completeness anymore, because you can define natural numbers. With that, you define the exact model of natural numbers, not something isomorphic or elementary equivalent to it. Exactly the natural numbers, up to an isomorphism.
Do you need some restrictions on the way you form mu's?
Like yes. X must appear in a positive context.
Okay, good.
Must be an even number of complements. Yeah. All right, how expressive it is? Well, so we started, and these are great topics for students. We started defining various logics as theories. First order logic, we can define equality. You know, in first order logic, you cannot define exact equality. You can define an operation which behaves like an equality, is a congruence, but it's not exact equality models. You have to extend the logic with equality. Here you can define the exact equality axiomatically. I showed you how lambda can be defined. Then different modal logics, actually Hoare logic as well, dynamic logics, LTL, CTL, CTL star. Actually, LTL is just one axiom that you add over some symbols. Separation logic, and more importantly for us in K, reachability logic, because that's what K is based on. And why we want this logic? Because eventually we want to generate proof objects for everything we do. All those blue boxes on the side, why should we trust them? Eventually they will generate proof objects, which you can check. Right, so reachability logic, which is the semantics of K, generalizes rewriting, right? Because rewriting is between terms, but now we have patterns. So why not have writing between patterns, more general? And we realized that, actually, early on, we realized that we can encode Hoare triples as reachability rules, where this is two patterns conjuncted. I take the pattern of the code and the pattern of the precondition, I conjunct them. Now I filter, I only keep the configuration that match both. And then reach the empty pattern, because in Horde triples, the code is empty at the end, and the postcondition, right? And now you can actually prove, for a language like Kim, take the axiomatic semantics and prove all the proof rules there as theorems based on the operational semantics using matching logic. With this observation, actually reachability logic a few years back, but now we realize that obviously reachability can be expressed like this, and eventually can be expressed as a fixed point. And now, yeah, so we can explain reachability logic is the point. Yes, Tom?
I'm just so, this is great work, but I'm just like, sorry, I'm smiling because like K is like incredible, but you've slowed down execution so much. So how much are you going to slow down verification?
Actually, let me show you something.
It just
I'll show you some numbers. Actually, I think that will get better verification.
okay, I'm waiting.
Good. Let me show you how verification works so far in K, right? So it works like any other program verifier. You get your program and your specifications, what you want to prove. And if they are Horde triples, you can translate them into reachability rules. But the point is that, and by the way, I can use your verification engines, and then I can generate, through the translation from Horde logic, reachability logic, proof objects in my logic. So I can use yours as optimizations, decision procedures, and everything, right?
I thought you were going to do all the proving in your...
No, we want eventually, but not for now. You know, we can do that. Actually, we do a lot of that.
Okay.
All right, so what's different is what happens under the hood, that the program verifier is now split into two nicely separated, cleanly separated components. One is the programming language semantics, and the other one is the actual verifier. And then what we do with the verification infrastructure, is really we reduce everything, or we take care of all the matching. And then we get down to proving static properties about the current configuration. And then we call Z3 there.
So what does this mean, though, in terms of, and just when you get to Z3, what are the formulas? What are the...
They are very, very close, almost identical to what you would get with a Horde logic-based prover and Lucas precondition.
And all the matching, all the problems we have?
No.
You're taking care of all of
Yeah, taking care of those outside.
what
The programming language construct, they all disappear. Yeah, because they are part of the matching. So I execute the program symbolically. In short, this is what happens. I execute the program symbolically with the operational semantics until I reach the point where I should check an assertion. And at that point, I generate an implication between the configuration I reach symbolically at that point and what I should prove. And then that's a matching thing. It's like unification. We decompose, eliminate all the constructs that you can handle outside, and then you get down to domains, natural numbers, strings.
So you're ground at this point?
No, symbolic, still symbolic.
Still symbolic, but what are...
No, by rewriting, you execute the rewriting, the semantics symbolically. I start with a symbolic configuration. I say that in the heap for program variable x, I have a value v. And there exists a v, I don't know what it is. And then I execute with the exact semantics, not with your camel backend. That's a different backend. With another backend. Yeah, it's a symbolic engine, yes. But the symbolic engine doesn't know anything about the programming language either. It just matches and applies the semantic rules that define the operational semantics of the language.
Okay, what are the theories you actually use of Z3?
Whatever Z3 gives us.
No, but I'm trying to understand, do you have quantifier alternation once you get down to Z3?
So we do not add any quantifier as an artifact of the semantic encoding.
But the specification may have.
But the specifications may have. And if they have, then we just pass them to Z3, whatever it is. Yes.
So when you do a content verification, you have to add pre-post conditions, looping variants, right? So in this case, would the user be adding them at the C level or in a case syntax?
So, right. So this arrow here, right, I can show you a demo later. So that arrow there may come with some sugar for your language. If you want to have looping variants in your language, we don't have looping variants in K. K doesn't know about loops, right? It only has reachability rules. So you need to desugar your looping variant into a reachability rule. And that happens outside. And whether that is correct or not, we don't guarantee anything.
But it would look like the surface syntax of the language, right?
Yes. Yeah. You are free to add whatever you want as far as you can generate a pattern, a semantic pattern out of it.
Do you have examples that use, say, separation logic?
Yeah.
How does frame inference work?
Frame inference.
Yeah. I mean, I assume that you know, I write a assertion separation logic.
Yeah.
And at
Actually-
various points, I need to compute, in order to apply the proof rules, I need to compute an instantiation
Yeah.
for the frame.
Yeah. So here's the thing. First of all, frame reasoning, as in separation logic, is not sound for all languages. If I have language constructs that rely on the size of the memory, and actually in the sour C semantics, the size of the memory, available memory, is an input. Right? Or if I have constructs that make sure that the whole memory is clean before I shut down or something like that, then it's not sound in general. But you can use the ... in your specifications. If I have a loop invariant and I say that I want to have X point to a list, and I don't care what's in the rest, I put ... if you don't care. If you do not put the ... it means that there is nothing else in the heap. And we do not automatically give you frame inference. Because that we cannot do that automatically. Unless you have some theorems about your language that is sound, and then, yes, you could use those. But we found that putting ... is not, for the frame, is not such a big price to pay.
I'm wondering if say, a naive encoding that I might try, if I encoded it down to Z3, I would end up in Z3 with an existential for the frame.
Yeah, actually, in matching logic, it's also an existential for the frame. But we eliminate that existential as part of the matching process before we get to Z3.
Do you eliminate it?
Yeah,
Okay.
yeah. If we do not send Z3 anything about maps in the heap. All right, performance. We compared it with a variant of VCC for separation logic developed by Madhu Sudan, a colleague at Urbana-Champaign and his students. So these are all kind of heap programs that we checked in order to compare it to separation logic based provers. And in particular for AVL insert, which is one of the trickiest properties to prove, the VCC modified by Madhu Sudan and his students to use their decision procedures for separation logic took 260 seconds to verify this property. And our prover completely took 280 seconds. But keep in mind with the actual C semantics that is quite faithful. It's right, so it's based on the semantics. So it's not too bad, right? Almost in the same category. And this is how it is split, how the 280 seconds are split. So execution, symbolic execution is like 210 seconds, and then reasoning, basically Z3, ends up being about
I like this slide.
70. Hmm?
I like the slide.
Yeah. And there are that many queries that we do. So we do lots of small queries. Almost every single rule may need a query as part of the matching, as opposed to one big query. So that's why I believe, of course I may be wrong, but I believe that actually such verifiers will incentivize people to actually optimize them because they can use them across all the languages, right? So people who care about functional programming then will also contribute to the verifier. And also the fact that you know that it's correct by construction, it's also good. You don't have to prove any soundness of the logic of the axiomatic semantics or the prover.
What you're saying is, if I write my semantics framework, it will be. I can't make a mistake in adding accidental axioms or something.
Oh yeah, then everything is wrong.
And that's because you've already done it.
Yes, actually the C semantics, even now we fix bugs in the C semantics as we find them. So Philip Wadler and his team just reported a bug. But then you don't have to go into the other tools to fix the semantics. I don't have to go into the verifier or model checker or symbolic engine to fix the same. It all comes from fixing in one place. And that paid off actually for us.
But wait, I have to trust K, the whole K.
Yes,
Right.
yes, now yes. That's why I wanted the logic so we can generate proof objects for everything we do. And then you can check. So you can take those 13 proof rules plus the 2 for mu, 15. You have 15 proof rules. You have a proof checker for 15 proof rules only. And now if the blue boxes in K generate proof objects for those, you don't have to trust K. K is out of the picture completely.
Right.
And the proof checker is not too hard to implement for those proof rules. It's actually a lot simpler than Coq, for example. Coq has 40 plus proof rules.
So that's a species, of course. Maybe Coq does something really great that you cannot in those other 25.
I would love to get into that, but actually we are, as I saw on that slide, different logics that we define as theories in matching logic. Now we are looking in inductive type theory, intuitionistic type theory. And I don't want to claim anything yet. We didn't publish anything, but we believe the same holds there. I can take, for example, the PTS, the pure type systems, and then define a matching logic theory. And you actually have fewer axioms than in the actual proof system, because I don't need to worry about weakening and things which hold by default in matching logic. And then prove the conservative extension theorem, that if you start with a proof task in the original logic, gamma satisfies phi, then with the matching logic, I prove exactly the same property for the translated encoding. So I cannot prove more things. It's a conservative extension. So if you stick to the object logic language, then you can use the generic proof system to get the same proofs done. Yes, I'm very excited about it, and I hope it is true.
Are things maybe more extensional in what you have? Like the equality is very extensional in what you have compared to what you might have in type theory?
Equality, so equality is definable in our case, right? So equality, you don't have equality by default. You can have if and only if, but if and only if and equality are completely different beasts. Equality can be defined, it's exactly equality, but if you're talking about extensionality in the sense of lambda, then you need to add an axiom stating the extensionality. Actually, even beta reduction doesn't hold by default. You have to add an axiom for beta there. Now I can start my talk. No, okay, I will.
It's an amazing, it's a giant, it's very impressive, right? It's a big project. You must have been working on this.
All my life, and that's what I will do until it works, until everything works. Yeah, because if this works, why should we do things any other way? I have absolutely no motivation to do things any other way if this works. So I'm stuck. All right, so for the blockchain, all we have to do now is to plug and play blockchain languages. And we started with one of the most used language in the blockchain space right now, which is the Ethereum virtual machine, which is a stack-based machine of the extremely simple language, a classroom project compared to the other languages that have been defined in K. So what we did, we defined it. It's all public. The nice thing about the EVM is that the developers provide 60,000 tests, which is great. That's what we need when we define the semantics. We need tests to test it. And we passed all of them. And Tom, the K-generated interpreter is only 8 times slower than the C++ implementation of the Ethereum virtual machine.
The Ethereum blockchain, so it's already
Exactly. They don't care about performance because achieving consensus takes like 100 times more. But what they wanted in the C++ implementation, actually we talked to the developers, what they wanted was clarity. They didn't want to have something efficient because they criticized us that, hey guys, we didn't try to make it efficient. Yes, we neither. So the whole point of the virtual machine was that different people look at the VM and they trust it. It's all based on trust a lot, right? So that's why it's not efficient. Yes.
How are these tests executed? In Remix or something? Where do you execute?
The tests?
Yeah.
So we use the exact same test harnesses that they have with the C++ implementation. They have some JSON files and they execute them. But it's not Remix.
So are you able to replay the whole history of the Ethereum blockchain?
We haven't done it, but we should. We haven't done it yet.
Why not? It would take too long, or is it?
I need a student to do that. Yeah, when the student comes, we'll do it. So we're driven by contracts here, and the contracts are about verifying smart contracts. So we quickly went into verifying. And these 60,000 tests were good enough for testing the semantics.
So did it test for gas exceptions and things like that?
For what?
Out of gas exceptions and all that?
Yeah, the gas is part of the semantics. The gas model is part of the semantics. And check, in all these tests, we check to consume exactly the same gas. And as a matter of fact, actually, the Ethereum Foundation right now is considering adopting this K semantics of EVM as the canonical specification of the EVM. And that's really nice. I'm so excited because that's how things should be. There should be formal specifications of this, not just words. Right, so what can you do with the KVM? So first of all, you can run a blockchain based on the semantics because only 8 times slower is acceptable in this space. And actually, a company, IOHK, has done exactly that. There is a test net now, which is like a blockchain that you can run you can compile your programs with Remix. Also has a Remix, it is connected to Remix. You can literally run your contracts on this blockchain. You don't even know that the virtual machine has been generated from the semantics. And why you want to do that? Well, just to make sure that the VMs are correct, provided K is correct. We don't know that. But actually, I know it has bugs for sure. But the idea would be that you do not write the code of the VM by hand. It's generated from something higher level. Another thing that we can do, and this is what we do mostly, where most of the revenue comes in our company right now, is formal verification of smart contracts. And this is our webpage. And then the Ethereum Foundation actually also gave us the first security grant, which was specifically to formally verify their Casper protocol. Casper is a proof of stake protocol, and the original version was run on a proof of work network. And it was a smart contract, which was the largest smart contract we verified, and they wanted to make sure that smart contract was correct. And then we verified it for them. That was part of the grant. And that's how we started actually doing business in this space. How long?
How large?
About 800 lines of Solidity. But when you get down to EVM, it's about 10,000 lines of bytecodes. Yes?
What kind of properties are people generally looking for?
So like the transfer function. The transfer function indeed gets the value V from account A to account B, provided you have enough balance and provided you don't do an overflow. This was one of the specifications. I think we had to write like 50 or so such rules for Casper. All right, and just in case you want to take a look under the hood, how things look like. So informally, people write protocols like that. That's part of the ERC20. They say transfers value from account to account. And then there is a note, transfer of 0 values must be treated as normal transfers. Right? So that's why that original program I showed you at the beginning was wrong. Right? It violated the specification. So what we do, we take such English descriptions and then we formalize them. So this, informal business, we formalize them in K using rules. And they look something like this. This is one of the specifications. This is the specification of transfer, how it works. But that is too high level. This is also related to your question. So it is too high level for EVM. Then we have, unfortunately, still a manual process to push that down to the level of the bytecode. We should automate that, but it's not automated yet. We push it down to the level of bytecode, and this is what we actually verify at the level of bytecode in the end. And whether this is correct, we don't know. But hopefully, this should be done automatically. Actually, what I'm trying to convince the blockchain community is that they should stop using languages like Solidity. They should use directly K. They should write, this is a transaction. That's how I like to write a transaction, not using Solidity code. Yes?
Yeah, so the thing on the right, so you wrote that.
This one here.
Reading the English.
Yes.
And then to win the grant, you have to convince people that what you wrote there corresponds to the
Yes,
English.
yes. Actually, yeah, we had to refine the agreement, the service agreements a lot. So now what we are doing, we are asking the company, the customer, to have a person dedicated to the project and a person who we can ask questions all the time. And that person should sign off that this is the specification before we start verifying the code. So we spend a couple of weeks with them making sure that this is what they had in mind. And actually, we find lots of errors at that level, as you know. When you formalize the things, you find lots of errors before you even go to the code. And that's why we want to do it then, because we don't want them to re-verify the code. We want them to fix the code, and then we verify the code.
But what I see there is like an XML thing.
Yeah.
So how do you, like the semantics of that are not defined either?
Well, this is the K thing, right? So this is the K cell. You see, you write there, and this dot 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 is the frame. This is the K rule.
Oh, the K rule.
Yeah, that's how we write those bubbles in K. We use XML, and many people hate that. So we are considering an alternative syntax.
But so this should correspond to your K definition in.
Yes, the K specification. So we do everything in K. The language specifications in K, the property specifications are in K.
So why is that? Then I don't understand.
Oh, because this is at abstract level that we can discuss with the customers and they understand.
But it should execute already. This is K, right?
Yes, and this is also K here. But this is K using a slightly different syntax. You see, we also have an alternative syntax. You can say K colon this or K in XML tags. Here, where is K? We don't. Oh, here is K.
But it's something different because you couldn't do it automatically.
Yeah, so they don't see this. The customers don't see this.
I just don't understand why you can't use the thing on that side
For verification? Well, because that is very abstract. When you talk about EVM, you have to go to ints being 256 bits. You have to look at the, you see, the return address. There is a return address keyword that matters in that word, but not there.
So then I don't.
There is a gap. I agree, there is a gap.
But get formalized.
So this spec here is huge.
But that's what you formalized, right?
Yes, but this is pretty mechanical. So this is what we formalize for them, and we have them sign off that this is the spec. And now we are responsible for this translation from here to here by hand. I wish we had an automated way to do it, but we don't.
Right, right. So but in your framework, you've like a real specification of the EVM.
No, but
None of.
yeah, because so here's the thing, right? So K is language agnostic. K is complete language parametric. But once you plug in a language, then your terms, your patterns, and so on are specific to the syntax of that language and the semantics, the syntax of the semantics of that language. You write patterns using that language. So that doesn't even parse in the EVM semantics. In the EVM semantics recognizes, these things like local mem, execute, log. There is a log. Right, so all those, yeah, so that's why it would be nice to have a notation, like Shuvendu said, to have a notation specific to your high-level language, and then generate all this automatically. But
What is the high-level language on this side? Is that
K. Oh, what is the language here?
instantiated with?
Right. K instantiated with the semantic entities that the English text refers to. It refers to accounts. Okay, so now we have accounts. There are these account cells. Then they refer to balances. There is a balance cell semantic component, right? So there are all these semantic components that they refer to in their English. Right? It's a formalization of their abstract language.
Is there semantics on those terms? Like, is there a case semantic that talks about?
So the case semantics actually is a set of rules. That's what the case semantics is. And in this case, this set of rules is exactly the specification of their protocol.
Okay. So you're defining a state machine in K, and that
Yes.
is the
That is what they meant,
specification
of what they meant for their protocol.
Idealized semantics.
Yes, exactly. And actually what I'm trying to convince people is that they should stop there. They don't need all this crap. Sorry for saying that. They should stop directly here, and you should use K as a VM and run contracts directly that way, and done.
But you picked a vocabulary on the left suited to this particular contract. I mean, if
Yes.
I have some other contract in mind, do you need another?
True.
So
Definitely
is
true.
the problem here that
Yes.
they don't have a workflow language? It seems like something is missing. What's missing? They don't have a workflow language, a formal workflow language?
Who, the customers
You
or?
said you did it by hand. Why? Because something is missing that you can't formalize. What's missing?
No. So something is missing. So how to go from the abstract semantics of what they want to do, which can be done in any language, versus how things work on the Ethereum virtual machine.
Yeah,
And we do not have that translation.
because the abstract language is not defined.
The abstract language, yes, is not defined.
It's not defined. That's
No.
the problem.
Yes. And
Up there, it's
this is its definition now. They are all the symbols are uninterpreted. The only interpreted thing is the rewrite rules. As Nikolai said, it's like an abstract state machine that describes what they had in mind over the implied syntax they had in mind.
So what's missing here is information with Solidity compiler. So Solidity compiler does exactly that. Right? So you start from a Solidity
Yes.
contract, and you have two artifacts formalized in case. So the Solidity to this abstract.
No, we don't have that.
You formalize the syntax of the semantics of Solidity in K, right?
Actually, no. We are working on it. We don't have that. Actually, we didn't need the semantics of Solidity in order to do all this work, because people don't care about Solidity. They know that the Solidity compiler is buggy. Actually, it has lots of bugs. Nobody trusts the Solidity compiler. So instead, what they do, they want to verify things directly at the bytecode level. Yes, you have to trust me that I translate correctly from here to here.
Wait. You mean they don't trust it, so they don't use it, so they write it in what?
They don't write it in anything. They write it in English. They write the program is written in Solidity. Then it is compiled using the Solidity compiler, which has bugs, to bytecode, and then we take that bytecode and verify it. But to verify it, we need specifications, and the specifications come from this process. But the bytecode, we don't touch their bytecode. Actually, the bytecode changes several times during the verification process.
So you start from a Solidity contract. If
Yeah.
you use a Solidity compiler to share EVM bytecode, and you compare that to your manual translation, there should be.
I'm executing that. No, I'm executing that.
But so the output of the Solidity compiler and your manual translation from the high-level spec, they should be the same thing, right? Ideally, if the Solidity compiler.
No. So the bytecode generated by the Solidity is just EVM bytecode.
Yes.
And that EVM bytecode can be executed with the semantics of EVM.
Yes.
Okay? And what we have here, we have these reachability rules, like Hort triples, if you want, over the functions that are implemented by that EVM bytecode that is generated by the compiler. And somewhere here, right, we refer to the transfer function, right? And this transfer function is coming from, the bytecode of that is coming from the compiler. But everything else here is written by hand, unfortunately.
But that's just checking.
Hmm?
That's, yes, right. So
It's an eyeball acceptance.
Plug in whatever Solidity generates or transfers.
Exactly, yes. Yes,
The thing you wrote here.
yes, and as I said, that happened several times during the process, because as we verify, we find bugs, we tell them. Then they modify the code, they send us a new version of the code, a new bytecode. And then we run exactly the same proofs, the same specifications, the same everything with the new bytecode.
And what you would like is a higher level language. They can write this automatically.
Right, but as he said, each protocol comes with its own, syntax, its own data structures, its own things, and those need to be formalized. I don't think there is any general language. I mean, that's what they try to do with Solidity, right? A language to implement all these things. So basically, you have to do it for each contract separately. So, which is why I believe that we can use directly K as a programming language here, because this is all executable. So this could be the definition of the protocol, an implementation, definition and implementation of the protocol.
So maybe I missed something. But how much do you capture in the high level? So for example, you capture the type system, how much, because you see there is int256 there, but you have many other integer types.
Right.
And you also have this distinction between the storage and memory. So
right.
I don't see any of that in the high
No,
level spec.
exactly. We don't capture any of those. No, you don't look at types, don't look at size of integers. But we do have a general notion of overflow, and those then translate by hand here. So yes, if we want to mechanize that, we'll need probably to add more information to the abstract language. But again, my hope is that people will get rid completely of this EVM thing and just have a K virtual machine that runs that thing directly. And then you don't have to worry about all of these problems. That's why I don't want to go into that. That's why I don't want to formalize this translation, because I don't want this. It's good business, but I don't want it.
I might actually say that if I'm a, well, tell me if this is inaccurate. If I'm an EVM expert,
Yes.
and I have some understanding of the way the EVM semantics is transcribed into K,
Yes.
then I should be able to read and write this
Yes.
stuff.
Yes. Exactly.
Okay, so the right is the truth. So I should just forget about this stuff.
Yes, you can write it directly here. Yes, I agree.
So I mean,
You and I and maybe a few others. But the people we talk to, they don't understand EVM at all.
But they're trying to really? I thought
No, they
were
don't.
trying to write-
No, they write things in Solidity, and even the code in Solidity is full of bugs. You just look at them 15 seconds, and you find immediately an overflow. Just look at it. Yeah, and that's the code they write, and they don't understand what's under the hood. Not my fault.
Yeah.
This is how EVM looks like. Right. And there are reasons why it should be like this, because it needs to be low level. And because you need to meter gas, basically to charge people. But if it must be low level, I would prefer something like this, like LLVM. And this is something we've done for a customer, IOHK, one of the founders of the Ethereum blockchain. They wanted an EVM. They wanted something that EVM should have been. So they asked us, okay, you don't like EVM, because I make it very clear to everybody that I don't like it. They said, okay, you don't like it, what should have that language been then? And I said, it should have been an LLVM-like language, human readable and so on. And then he said, why don't you design such a language, and then we'll incorporate in the next generation of blockchains. And this is Yele, which is literally an LLVM for the blockchain, a simplified LLVM, right? All integers arbitrarily large. And what's nice about it, and I'm particularly super excited, is that there has been no implementation whatsoever for Yele, only a formal specification. And the VM is generated from it. There is also a testnet based on it that was started in July 18, and people started using it. There is also a compiler now from Solidity to Yele. and I hope that more and more blockchains will adopt it. And again, absolutely no implementation. Several other languages we are defining semantics for, also WebAssembly. If anybody's interested in WebAssembly, I would love to talk about. I would like to.
Is a friend of mine who works on Affinity.
Oh, perfect.
Wanting to use WASM.
Yes, I would love to have a very solid reason to define WASM completely. We have a prototype, but I hope we go all the way through. Let's talk about that. Right, protocols, and there is an LLVM backend in the works, which promises an order of magnitude performance over the OCaml. Semantics-based compilation, we like to generate a compiler also from a semantics, not only an interpreter. And we have a prototype. And the idea is to generate a semantics for your program by refining the original semantics of the programming language based on your program, and then use the normal backend that we have. And a prototype that works with IMP takes that program into this program over a programming language with 1, 2, 3, 4 constructs only. And these are the rules, 7 or 8 rules. And this adds more than an order of magnitude performance. And the next step is to generate proof objects for all the blue boxes. And there's a formal method center that we want to create, which I thought I could talk about, the University of Illinois. If you're interested in collaborating with us, I would be very glad to talk about. And done.
Okay, thank you. We asked too many questions.
No, you asked the right questions, and I talk too slow.
Philosophically, so ACL2 also had this executable semantics, right? How does this fit into like ACL2's?
ACL2?
Yeah, it also had an executable operational semantics. You can execute things and also
Yeah.
have it. Theorem proofs.
I think the same philosophy. Yes, yes.
What do they lack?
I don't know. I wanted to have a logic, everything to be driven by logic in the end, and to be an operation. In ACL2, my feeling when I looked at the programs was that they were like functional programs that you write, right? And I like functional programming actually. The K backend is implemented in Haskell, 70,000 lines of Haskell. We love functional programming. It's just that I would like to have something that is a specification language looks like an operation, like a semantics, and it has a logic underneath, right, to do proofs and to generate proof objects. But I think it's the same philosophy, yes. And there are several other frameworks like Racket, like SpoofX. They all try to do the same things.
So if you try to define, for example, the Haskell in K, what do you do like with type checker, for example? This is like
Yeah, so we define type checkers exactly the same way. A type checker is a semantics where the programs evaluate to their types. You can have like a small step computational semantics.
Is it complicated?
Yeah, so we have defined actually. We have defined let polymorphic, the Damas-Milner type inferencer, exactly the rules.
Let's take the rest.
Thank you. Thanks.